Okay, good morning, everybody, and welcome back from the spring break. How was your spring break? I hope you had fun and relaxation, and you're now ready to embark to the second half of the semester. I know there might be a lot on your plate right now that prevented you from enjoying the entire spring break. But for one, for Cal 2, we have test number 3 coming up, and you have homework, written homework. I think it's written homework 3 due on Thursday. So that's a lot, but I hope you still found a couple of days to relax because that's also important. So now going back to our business, I did not prepare any specific worksheet for now because I look at your calendar and it says it's a review for test number 3. So for today, I'll be counting on you to send your questions, be it from the practice test or from the homeworks, and let's try to answer them. But if nobody will ask some questions, then I'll just gonna give you some generic problems from some topics over the topics, right? But it will be great if you can send me your questions, right? So I see here that Christina already sent a couple, so thank you, Christina. Is this from the written homework? Okay, great. So that being the case, then I will not be including this in the worksheet that I'm going to upload later because I don't want you guys to just copy it over. Of course, you might say that there's the video for it, but at least in the video, you can listen to the explanation for every part of the solution compared to just being able to copy it from a worksheet. So yeah, I don't mind if you will do so, but at least try to learn why we did all of the steps or what is the reason going from one line in the equation to the next. So that's the whole point in here. So let me see. The first problem is the integral of x cubed over root of x squared minus 1 dx, right? So probably in the exam homeworks or quizzes, you might not be told exactly what method to use on a particular problem. So it will be helpful if you can distinguish when is a certain technique of integration be helpful. So, but in analyzing the given integrand, always start with at least on your head, try to do u sub. That's the simplest, and that might work. You might be surprised that that will work unless you were specifically told to use a specific method. So in this case, our candidate for u is x squared minus 1. For that, you will need a du equal to 2x. You can get that from the numerator. You can split this as x times x squared. So I guess u sub will work in here, but yeah, you can choose to do it. But he wants some help with trig sub, so I'm going to solve this with trig sub, though I think u substitution with some algebraic manipulation will work for this particular problem, right? So for the u sub, you look at the expression inside the radicand, and depending on how it looks like, you use a certain trigonometric substitution. If it's a squared minus x squared, you need a sign substitution. If it's x squared plus a squared, you will need a tangent substitution. But if you have the case x squared minus a squared, like what we have here, we will use a secant substitution, right? And you will see later why that is the case. So here I will let x to be equal to secant theta. So then dx will be secant theta tangent theta d theta. So that will be the replacement for dx. And then what we'll have here is, oh, I have an x cube here, but I knew that x is secant theta, so I'll have a secant cube here all over the square root of secant squared theta minus 1 times dx, which is secant theta tangent theta d theta. So the thing about trig sub is we are hoping that after simplification, the integrand will be much simpler than what we started with. Of course, there will There will not be any square roots anymore, but hopefully we'll get an integrable form. If you're getting a non-integrable form, then it would be helpful to check your substitution. One common mistake students make is that they forget to change the differential. So dx must be properly replaced by the differential computed right here. Well, Kevin is asking, how did I know to use secant theta? Well, it's I'm counting on the use of Pythagorean identity over here. If you remember, there's a table. So if you have an a squared minus x squared, you let x equals a sine theta. If you have x squared plus a squared, you let x be equal to a tangent theta. And if you have x squared minus a squared, you're going to use x equals a secant theta. And you will see here why I wanted to use secant theta, or what's the rationale behind this substitution formulas, or this table of proper substitutes, right? The essence is that we are trying to use Pythagorean identities to get rid of the square root. So I'll just simplify this first, the numerators. So I'll just multiply them over. So I'll have secant to the fourth theta, tangent theta, all right? All over, I'll have the d theta here, a square root here. And this is where the choice of x being secant theta comes into play, because I have secant squared theta minus 1. If you go back your notes from trigonometry, you see that secant squared theta minus 1 is actually just tangent squared theta from the Pythagorean identity. And that's exactly the reason why whenever you have this form, you will use a secant theta, okay? And that is extremely helpful because now we get secant to the fourth, tangent theta, the denominator being a perfect, or being the square root of a perfect square, can be written as just this. So the radical is gone. And hopefully that will make the integral much easier. So we'll have the integral of secant to the fourth theta d theta, which is a power of an even power of secant, okay? I guess if you have an even power of secant, you go back to integrating powers of trig functions. So that is usually the case whenever doing trigonometric substitution. Be ready to be dealt with powers of trig functions. So you should also know that particular section in order to use a trig sub here. So the strategy is I have an even power of secant. I can write it as secant squared theta times secant squared theta, and then write one of the secants in terms of tangent. So remember that secant squared from the Pythagorean identities is 1 plus tangent squared theta. Or is it the right strategy? Let me think a bit. Yeah, I think that's right. Because here I can carry out the multiplication. So I'll have secant squared theta plus secant squared theta tangent squared theta d theta. All right. And then I'm integrating a sum. I can integrate them term by term, then just add the answers up. And I will do that because I know how to integrate secant squared, right? The integral of secant squared is just tangent theta, right? So this would be tangent theta plus, do you guys still see my screen? Because from my laptop, I cannot see my screen is frozen. I already wrote something after the integral. Okay, sure. I'm gonna retry sharing it again. Okay, now you should be able to see it. I'll go back here. All right. So I got the sum here. I integrated the first term. Integral of secant squared is tangent theta. So we'll be left with the integral of the second term. But for the second term, I can let u be equal to tangent theta. And then du will be secant squared theta, d theta. And that's the reason why I am comfortable with this form, because I knew that I would let tangent to be u. That will require a secant squared as the du, which is completely set up in here. So I'll have tangent theta plus integral of u squared du. Good. So we'll have tangent theta plus u cubed over 3 plus the arbitrary constant c. And then we revert to theta, means we'll have tangent theta plus 1/3 tangent cubed theta plus c. And we're not yet done because we need to revert to the original variable x. Now to go back to x, we recall the substitution that we made earlier. Remember, we let x be equal to what? Secant theta, okay? And from SOHCAHTOA, secant is what? Hypotenuse over adjacent, because secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, right? And you can think of x as x over 1. So if you draw a triangle, say the right angle is here, if theta is here, then the hypotenuse is x, adjacent to theta should be 1 unit. So the third leg would be what? X squared minus 1. And remember, this is an expression in the original integral that we started with. That's a signal that you had the right triangle, or you drew the right triangle. So you should meet again the radical originally involved in the problem as one of your legs. Okay. So, and there we go. We got that here. So I'm at least confident that we have the right one. Okay. So going back to x, tangent theta. Tangent theta is opposite over hypotenuse. Opposite over adjacent. So opposite over adjacent. So it's going to be root of x squared minus 1 over 1, right? Plus 1/3 cube root of x, square root of x squared minus 1 over 1 to the 3rd power plus c. Of course, it's better if we have written it this way. Okay. Does that make sense, guys? Is that okay? Okay. Yeah, you had another question, Christina, here. Trigonometric substitution again. But if you look at the radical involved in the denominator, you can let x be equal to a, or maybe let's work it out. Because I was thinking to give you another problem, which is similar to district substitution. But okay, doesn't matter. Just go with this. But I won't answer it completely. I'll just set it up and then just let you guys think about what to do next after we perform all the trigonometric manipulations. So, or substitutions rather. Okay. Now, so you want to integrate this. So we look back at our forms. Remember that here our form is a squared plus x squared. That's what we got, right? If you consult the table that I wrote earlier, this will tell us that x should be chosen to be a tangent theta. So here a is equal to 2, right? So because here this is a squared. So a should be equal to 2, the square root of 4. And you had a plus, so we knew we'll get a tangent. So here I let x be equal to 2 tangent theta. All right. And then dx will be 2 secant squared theta d theta. All right. Now, I will not solve the entire problem, but just to guide you later, when you go back to the original variable, so you remember, you look at your substitution statement over here. You can write it as x over 2 equals tangent theta, right? So your triangle should look like this. If you decide here's the right angle, here is theta. Remember, tangent is opposite over adjacent. So opposite theta should be x units. Adjacent to theta is 2 units. So the third leg being the hypotenuse should be 2 squared plus x squared, which is basically 4 plus x squared, which is the original radical in the original problem. So we knew that, okay, we are on the right track. We had the right triangle because I already saw this in the original integral. So that's one nice indication that you had the right triangle, okay? Now let's perform the substitution then. So dx will be replaced by this guy. So we'll have 2 secant squared theta, d theta. That's the replacement for dx. X squared will be replaced by the square of this. So we'll have 4 tangent squared theta times 4 plus 4 tangent squared theta. So here you will see why you need this extra factor 2 in the trigonometric sub. Because if you go to the integral, or to the denominator of the integrand, so let me just copy the first few expressions. Okay, here I can factor out the 4 and be left with 1 plus tangent squared theta. So if you forgot to include a 2 in here, you will have a problem isolating a 1 plus tangent squared theta. Remember, the Pythagorean identities involve the number 1, right? Because it is based off of sine squared theta plus cosine squared theta equals 1. So you really need a 1 added to a square to the square of the tangent. So it's important that you include the coefficient 4 there in your substitution. So what will happen will be this. You'll have 2 secant squared theta d theta all over 4 tangent squared theta. Then this 4 will come out of the square root as a 2, right? Then 1 plus tangent squared theta. And then you'll have this guy all over 4 tangent squared theta times 2. And then this would be square root of, if you recall your trigonometric identities, 1 plus tangent squared is secant squared theta. So finally, you will get 2 secant squared theta d theta all over 8 tangent squared theta times secant theta d theta. Okay, and you do the simplifications. I'll leave to you the rest of the solutions. Okay, I guess that's fair, unless you have questions how to proceed. I guess what you need to do next is to, of course, cancel the secant in the denominator by one of the secants above. Oh, yeah. Thank you, Kevin. That's a typo. Yeah. Only one theta. Only one d theta. If you have 2 d thetas, then that would be a double integral. But actually, it will still not make sense. So anyway, that's it. You cancel the secants, and then you'll have a secant theta over tangent squared theta. We don't have any way to integrate that by looking at it simply as a combination of powers of trig functions. So after canceling the secant, maybe what you can do is to write everything in terms of sines and cosines, right? Secant is 1 over cosine, tangent is sine over cosine. Play algebraically with the sines and cosines, and then you'll have a U substitution problem. Okay. So I leave that one to you guys. Is that okay? Oh yeah, Christina. Yeah, actually that's also hard because you need to manipulate the trigonometric expressions to the simplest form before you can proceed with the integration. So again, here, I guess what you need to do, cancel the secant with one of the secants above. So we'll have secant theta over tangent squared theta. You can take 2/8 out of the integral if you want. So there would be a 1/4 outside. And then on the secant over tangent squared, write them in terms of sines and cosines. Replace secant by 1/cosine, replace tangent by sine over cosine, and then simplify by canceling some things, and then you'll have a U substitution problem in front of you. Okay, let me know if if you find some difficulties there. All right, how about the others? I only got 2 questions from Christina over here. How about you guys? Do you have questions? Okay, while waiting, let's look at this particular problem. I guess this is from the practice test. Find the arc length of f of x equals x squared over 2 over the interval 0 to √3. Okay, yeah, Brian, can you send a screenshot of that problem? It would be great if you can do so, because I don't have a copy of homework 3 right now. Okay, so while waiting for that, let me work this problem out for you. A student of mine from the other lab told me that this is in the practice test, and he was a bit confused because he thought that arc lengths is a thing of chapter 7 or chapter 7, and thereby not included in test number 3. But it turns out that in order to evaluate or to find the arc length of this function over the given interval, you need trigonometric substitution. Okay. So here, if you recall, back from chapter 7, the arc length is the integral from a to b of the square root of 1 plus the derivative squared. So I hope you guys still remember this. This is another manifestation that math is a sequential subject. So that means you might encounter, or you might need tools from previous chapters in order to answer a problem from the current chapter, and that is the case here. Okay, so this is the formula for the arc length. So we need to compute for the derivative. F prime of x is equal to, oh, it turns out to be nice, it is just x. So that means f prime of x quantity squared is equal to x squared. Okay, now so we can have the arc length to be the integral from 0 to √3 of 1 plus x squared dx. And now you see that if we were in chapter 7, we will not be able to solve this because no U substitution will work for this integral, right? If we don't know trig sub yet. So when we dealt with arc lengths before, we took advantage. We saw some examples wherein the resulting expression inside the radical is a perfect square. So that's why we were able to get rid of the square root back then. But that's not the case here. We have 1 plus x squared. It's not a perfect square, so it cannot get out of the square root. So Kevin is right. So for this particular problem, what we can do is to do trigonometric substitution, letting x equals tangent theta. So here I'll let x be equal to tangent theta. That means dx is equal to secant squared theta d theta. Okay. Now, if you notice that in the previous test, I guess we had been a little strict about notations. So when you change the bounds, when you change the variables, you're expected to change the bounds, right? So, and then for me, of course you can do that, but for me, I don't want to keep track of all those changes in the bounds, where in the end I will just go back to the original variable and so on. So to avoid getting deductions for not keeping track of all of the changes in the bounds, what you can do is to forget about the bounds and then just put them later. I mean, we can evaluate the indefinite integral first. So I'll just say, okay, now I'll solve the indefinite integral first so that I don't need to change the bounds every step of the way. So here I'll just have square root of 1 plus tangent squared theta. Dx is secant squared theta d theta. And you see, if you insist on working with the definite integral as a whole, then that means your bounds here should be different from 0 and root 3. You need to plug in x here and see what's the value of theta, because the bounds here should be bounds for theta. But I am circumventing the rules now by just saying, hold on, I will not compute the definite integrals. I am just computing the indefinite integral right now. And then I'm just going to use the fundamental theorem later when I go back to the actual arc length. Because anyway, I'm going to go back to the original variable x anyway. So that's one way you can circumvent around that rule. Okay. Now again, the reason why we pick x to be tangent theta is so that this square root will have a secant squared theta inside of it. Okay. And then the integral will be gone because the radicand is a perfect square. And then you have two options here. You can do integration by parts, but I guess you were told that you can memorize the formula for secant cubed, right? So I will use that, or assume that you memorized the formula for secant cubed. Otherwise, you need to do integration by parts here. You let u be equal to secant theta, and then du is dv is secant squared theta, and you will get the integral. But anyway, if you do that, or you memorize secant cube, the integral for secant cube theta, you're gonna get 1/2 tangent theta plus ln of the absolute value of secant theta plus tangent theta plus c. Let me check if I had the right integral. Because honestly, I don't like memorization. So if I am to solve this, I'll just do integration by parts. But anyway, yeah, it turns out this is right. Okay. Oh, sorry, the first term should be secant x tangent x. So that's why I should be doing integration by parts, because I'm terrible at memorization. So this is secant theta, tangent theta. Okay. All right. And then now we need to go back to the original variable, but remember that we had this substitution. We let x equals tangent theta. The tangent is opposite over adjacent. X is also the same as x over 1. And then draw a triangle. If we decide that the right angle is here, theta is over here. So that means x is opposite, 1 is adjacent. The hypotenuse is 1 plus x squared, which is what we got in the original integral. So we're on the right track, at least as far as the triangle is concerned. So we'll get 1/2 secant theta. Secant is 1 over cosine, so it's going to be adjacent over so that is hypotenuse over adjacent. So that means we have root of 1 plus x squared times tangent theta, which is x, plus ln of the absolute value of, again, secant theta. Or I forgot the 1/2, sorry. There should be a 1/2 there. another 1/2 there. That's from the formula. So that's 1/2 ln of secant. That's root of 1 plus x squared. Tangent is just x plus the arbitrary constant c. Okay, so therefore, the arc length is equal, remember, to the integral from 0 to √3 of root of 1 plus x squared dx. And now we know an antiderivative for this guy, which is given by this. So we'll have 1/2 root of 1 plus x squared times x plus 1/2 ln of the absolute value of 1 plus x, root of 1 plus x squared plus x evaluated from 0 to √3. So yeah, that's where the bounds will come in again. So I'll do the plugging in. What will we get? So we'll get √3/2 times, I'll plug that in, √3 squared is 3 plus 1, that's 4. Square root of 4 is 2. So I'll have a times 2 here. Plus 1/2 ln of the absolute value of, again, I'll have a 2 plus √3. Okay. Minus, you plug in 0. If you plug in 0 here, this will become 0. If you plug in 0 here, this is 0. 0 squared is 0. So root of 1 is 1. This would be ln of 1, right? But ln of 1 is just 0. So everything will be 0 when we plug in 0. So here we go. We got the arc length. So this would be √3 plus 1/2 ln of the absolute value, or you can just drop the absolute value because 2 plus √3 is positive. Okay, does that make sense? Solution is a bit long, but I hope the process makes sense. And this is a reminder that you cannot just roll out everything from chapter 7, because if your professors would like to test your understanding of the material, then they will assume that, oh, you guys should still know chapter 7. So let me throw in a question from chapter 7 that will require a technique from chapter 8 to be solved. So here we go. So at least the basic formulas from there, right? Okay, now, so if you don't have any questions for the previous question, I'm going to go to Brian's question. It's problem 10 from the written homework. Okay. So we get, we need to evaluate the integral of 7x cubed plus 2x squared plus 3x minus 4 over x to the 4th minus 1 dx. U substitution will not work here because our usual suspect for u is the denominator. If you let u to be the denominator, then you will need a 3x to the 4x to the 3rd power as your du. But obviously, you have more than that in the numerator. It's going to be messy. I don't think it can be done. So we'll do partial fraction decomposition here, because we see that, okay, the top is a polynomial, the denominator is a polynomial. So probably probably partial fractions will work here. First, check whenever doing partial fraction, make sure that the degree of the denominator is larger than the degree of the numerator. And that's the case here. Bottom has degree 4, top has degree 3, so we're good to go. Next step is to factor the denominator completely. So here we have 7x. I'll just copy the numerator. Now I'll go to the denominator. I can first factor it as x squared minus 1 times x squared plus 1. Or let me reorder them. Okay. Dx, right? So because this is the difference of two squares, The first factor is irreducible. We cannot factor that anymore. But the second factor is still factorable. So that because that is again a difference of two squares. So I'll have x plus 1 times x minus 1. And remember, in the partial fraction decomposition, uh, the partial fractions will depend on how the factors in the denominator look like. So for instance, here, the first factor is an irreducible quadratic factor. So it is not repeated. It appears only once as a factor. So it gets one partial fraction itself as the denominator. This is degree 2, so the numerator should be 1 degree less. So this is quadratic, so the numerator should be a generic linear function. That's the rule, okay? So whatever you have in the denominator, or actually if it's a simple factor, it goes into the denominator of one of the partial fractions, and its numerator would be 1 degree less than its degree. So it is degree 2, numerator should be degree 1. And then the next factor is a simple linear function, a non-repeated linear function. So it gets one partial fraction. And again, the numerator should be 1 degree less. It should be a generic constant. Let's call it d. Why is that the case? Well, again, this is linear, degree 1. So numerator should be degree 0. And degree 0 is simply a constant. All right. You could use C, but I'm reserving C for the constant of integration, for the arbitrary constant after integration, so I use D. And a similar case will happen for x minus 1. It will get one partial fraction with a generic constant on top. All right. Now, can we do the integration right now? Maybe let's solve for the values of the constant first. Let's see. Now we want, recall we want this to happen. So I want this expression. Okay. So I will solve for A, B, D, and E. Right? So we want this to be true. Oops. We want this to be equal to this. Decomposition. All right. So if I do cross multiplication or if I multiply everything or both sides by x squared plus 1 times x plus 1 times x minus 1, we'll get this. So what I'm doing, what I did here is cross multiplication, meaning I multiply both sides by this entire thing, right? So that will be canceled on the left. On the right, we'll have ax plus b times x plus 1 times x minus 1 plus d times x squared plus 1 times x minus 1 plus e times x squared plus 1 times x plus 1. And this equation should be true for any x. And we'll take advantage of that fact, right? That this should be true for any x. So you can give any x value that you want. So say if I will let x be equal to, say, -1. If x is equal to -1, then what will happen? Plug in -1 to the left side. So we'll get -7 plus 2 minus 3 minus 4. Okay. So I plug -1 into here. I got this. Let's simplify this. So this would be -5 minus 8, -12. So let's just replace that by -12. Okay. And then we plug in -1. If I plug in -1, this will be 0. So first term vanishes. When x is -1, we'll go here. So we'll have d times 2 times -2. Is that correct? 1 plus 1. I hate doing arithmetic, so kindly check my work here. I guess that's correct. So from here, we get -12 equals -4d. So that means d is equal to 3. All right. Then we give another value for x. Let's try x equals 1 this time. Okay. If x is equal to 1, we'll get 7 plus 2 plus 3 minus 4. So that's going to be 12 minus 4. So I guess we'll have 8 equals. Plug in x equals 1. If I plug in x equals 1, this will be 0. Oops. This will be 0. So entire first factor goes to 0. X is 1, so this also goes to 0. So what will remain would be the third term. So we'll have e times 2 times 2. So that means 8 equals 4e. That means e is equal to 2. So we're halfway through. We know the value of d and e now. So let's try to find the values of a and b. But unfortunately, we cannot pick any real number that will make some of the terms vanish. So I guess we don't have a choice but to plug in arbitrary values for x. So, and that is valid because the equation should be true for any x. So for instance, if I will let x to be equal to 0, that's the easiest choice, at least for me. You can show off and pick any x value that you want, irrational fraction, decimal, big number, small number, or whatnot. That's your pick. But I'll stick with 0. So when x is 0, I'll get -4 on the left. On the right, I'll plug in 0 here, so that's going to be 0. So we'll have just b times 1 times -1 plus d times 1 times -1 plus e times 1 times 1. All right. So we'll have -4 equals -b. And then we'll have -d. But we already knew what d is. D is equal to 3. So I'll use that value. Then we also know what e is. So e is +2. So we'll get that. So we'll have -4 equals -b minus 1. So that's going to be what? -3 equals -b. So b is equal to 3. Okay. And then we can go ahead and use another value for x. Say if x is equal to, say, 2. If x is equal to 2, oh, that's a big one. If x is equal to 2, then we'll have 7 times 8 plus 8 plus 6 minus 4. I hope I did the calculations right. So it's going to be 56, 64, 70, and then 66. It's going to be 66 equals, we'll need to plug 2 in here. So we'll get 2a plus b. So I'll get 3 times 1 plus d times 5 times 1. Good question, Kevin. And I like your term killer value. It doesn't matter what values you use, even if it's not the killer values. And I will now use your term killer value. Yeah, it doesn't matter what values you use, as long as you get the right A, B, D, and E, then you're good. Actually, you can also solve this using. Oh, okay, that's fine. You can also use other techniques like solving solving linear equations. You'll have a 4x4 equation here, and that's perfectly fine. So, okay, and then I think I'll just solve for E here. So it's up to you. There are many ways how to kill a cat, so it's up to you. It's your choice. So you have E. Oh, sorry, it's just killing a cat is just an idiomatic phrase, so not to be taken literally. So we'll have 5 times 3. Okay, so we'll have 66 equals 2a. We knew b is 3 times 3. What is d? D is 3. So we get 15 here. Then I remember e is 2, so we get 1030 here. So we get a plus 45, plus 45. So we'll get a 21 here, equals 2a plus 3 times 3. Divide both sides by 3, so we get 7 equals 2a plus 3. Okay, and then we'll get 4 equals 2a. Finally, a is equal to 2. Okay. Actually, another thing, this equation is not only true for real values for x. You can also take x is equal to I if you're good at complex numbers. And why do I? What advantage will it give us? Well, if you let x is equal to I, so this would be I squared. But remember, if you're familiar with complex analysis or complex arithmetic, I squared is -1. -1 plus 1, so that's 0. This is 0. That's a killer value. So you could also have chosen x equals I or -I. Okay. So going back to our big problem. Okay. And remember, we want to evaluate this integral. And we said this is equal to this decomposed form. All right. Oh, oops. I thought I copied this. Okay. And then all you need to do is to plug in the values of a, b, d, and e. So a is 2x. What is b? B is 3 over x squared plus 1. D is what? D is 3. And then E is 2. All right. For this one, I guess it would be good to split this into two, split the first term into 2 terms. Maybe write it as 2x over x squared plus 1 plus, let me see, 2x, yeah, 3 over x squared plus 1 plus 3 over x plus 1 plus 2 over x minus 1 dx. And I will leave the rest to you guys, but I'll give you a hint. For the first term, you can use a u substitution. You can let u to be equal to the denominator, x squared plus 1. Because if you let u to be equal to x squared plus 1, du will simply be 2x dx, which you already got in the numerator. Be good, u sub. For this one, you need the integral that yields inverse trig. So the integral of, remember that the integral of 1 over x squared plus 1 is simply arctangent of x. So you get that. And then this is just an ln. This will just result into an ln. So I guess at this point you should be good. But as a disclaimer, double check my arithmetic. You don't know. Maybe I slip up or I committed some arithmetic errors in my solution for A, B, D, and E. So check it out and see that this really are indeed the constants you're looking for. All right. So do not quote me on this. Check the solution. All right. Oh, Robert has a question. Let me see. Robert, I haven't gone through number 2 on the written homework. Can you send me a screenshot of the problem? I don't have a copy with me right now.
Yeah, let me take a picture of it on my phone real quick.
Yeah, sure. Go ahead. Oops. Okay, so here you got this. Okay, so for that problem, let me see how we can deal with this. X plus 2 raised to x to the second power dx. Yeah, I guess you can, as you started doing here, you can expand the integrand. So you get x squared plus 2 times x times 2 raised to x plus 2 to the 2x dx, right? So for the first term, it's easy. You can integrate x squared easily. For this term, well, you can let u to be equal to 2x, right? So here you can let u be equal to 2x, du is 2 dx, and then you will have what? Something that involves 2 to the u, right? And that's just simply an integral of 2 to the u. Du is just 2 to the u over ln 2 plus the absolute plus the arbitrary constant c. But of course, you'll have a constant here. But essentially here, u sub will also be sufficient. Now in the middle term, here you will need integration by parts. You can choose this to be your u. You can choose this to be your dv. Okay.
Thank you.
Yep, I hope that made sense. Yeah, u sub for the last two terms, and then IBP on the middle term. Okay, guys. Any other quick question, because it's already 3 minutes after time. No other question for now. So hopefully by Wednesday you'll come up with more questions. I'm thinking. I was told that you already finished your your test review in the class today. So probably on Wednesday you will start chapter 9 on the lecture. So we have two options: either start with chapter 9 next time, or answer some questions that you might have for the written homework or for the practice test. Oh yeah, Christina, we could also go a little bit about section 8.5. Yeah. Though section 8.5, it's numerical integration. So I guess it's more of a formula-based type of scenario. But let me see. Yeah. But a more interesting thing about chapter 8.5 is about theoretical error bounds. So maybe I'll go with quickly on some questions about applying the formulas for numerical integration, but we can devote more time on developing an error bound or error estimates. I think that's a challenge for section 8.5, because otherwise you'll just need to memorize all the formulas there. Okay? So I guess that's a good plan, but hopefully you come back on Wednesday with more questions, hopefully for test 3, because I know you are, or you should be in the middle of your preparations for test number 3. Okay, guys? So thank you for coming today. Enjoy the rest of the day. Let's see each other again on Friday. Bye, everyone.